Welcome. In this session, we are going to look at a couple of examples illustrating the use of differentials. So one of the main uses of differentials is in approximations. So let me illustrate that by doing what engineers call a back-of-the-envelope calculation. We are going to estimate the fourth power of 2.003. Of course, 2.003 is approximately 2. So 2.003 to the power 4 is approximately 2 power 4 or 16. You can think of the differential approximation as giving the next few decimal places. So it gives you as many decimal places as there are in x roughly. Of course, there will be more decimal places in the function. We are ignoring that in our approximation. We are dealing with the fourth power function. So let's calculate the differential of x power 4. It's the derivative 4x cubed times dx. I think of 2.003 as starting at 2 and changing x by 0.003. So x is 2 and dx is 0.003, which means the differential is 4 times 2 cubed times 0.003. 2 cubed is 8 times 4 is 32 times 3 is 96. So differential is approximately 0.096, which means 2.003 to the power 4 will be approximately the starting value of the function. That's 2 power 4, that's 16, plus the differential, which is 0.0096, or 16.096. I said that differentials are nowadays more commonly used in theoretical work. There's a very simple illustration of this. We will again do this numerically, but there is a simple idea that will also illustrate some of the concepts behind derivatives and approximation properties. We will look at the differential approximation to the amount of material in a spherical shell. So like say the outer skin of a ball. I have a thin spherical shell with a diameter of 10 centimeters and thickness of 2 millimeters. I want to estimate volume of the material in the shell. Of course, you can calculate the inside volume and outside volume and subtract. To make a quick approximation using differential, the volume formula for a sphere is 4/3 pi r cubed, where r is the radius. Its differential will be the derivative of 4/3 pi r cubed, which is 4/3 pi times 3r squared, or after simplification 4 pi r squared, times dr. If the diameter is 10 centimeters and the radius is half of that, 5 centimeters, the thickness is the change in the radius, 2 millimeters or 0.2 centimeter. So the differential, there's a change in the volume of the sphere, will be 4 times pi times radius squared, that's 5 squared, times dr, that's 0.02. 5 squared is 25 times 4 is 100 times 0.2 is 20. 20 times pi, if you approximate pi by 3.14, will be 62.8. The volume of the shell will be approximately 62.8 cubic centimeters. Note that the differential of the volume is the thickness times the surface area of the sphere. The surface area formula is 4 pi r squared. So basically, the differential approximation is that the change in the volume of the sphere is roughly the surface area times thickness. Of course, if you had a flat object, this would be exact. For a curved object, it's not exact. So a differential approximation basically codifies these kinds of approximations in general and gives us a way of calculating such approximations.